Welcome, this is 48F video 1 and we're talking about laws of motion. Laws of motion will take two sections. We'll have F and G. We're going to start talking about the concept of force, and we need to clear up some things about that. And then we have Newton's laws of motion. We'll talk about inertia, mass and weight. And then finally, towards the end of this section, we'll talk about friction. In the next section, we'll talk about the application of all this work to two systems called statics and dynamics. Let's look at this next slide. Sorry, I'm in the wrong place. Let's look at this next slide. Bang. So this next slide shows the concept of force, and we say that there are two basic kinds of force. They're so-called contact forces. These are touching, pushing or pulling, where one object is physically touching another object. And then there's field forces, which are gravity and magnetism and electrostatics. Now I have to be honest and say that in reality, all these forces are field forces. When I hold something in my hand, what really happens is that the electrostatic forces around my finger's atoms press against the electrostatic forces around the atoms of the object. And so it's again electrostatic field interacting with an electrostatic field. So they're really all field forces. But clearly, if I appear to be holding something colloquially, I can say, well, that's different than having magnetism, a magnetic force extending over several centimeters. So we colloquially divide these things up into contact forces and field forces, but just put in the back of your mind that even the contact forces are also field forces. This next bit is often misunderstood, I think partly because we do forces so early in our careers when we are just given simple views of things, and so the detail's not given, and then later on it's assumed that we know this detail and we don't. But when we look at forces, it turns out that they always come in pairs and they always interact between two objects. So for instance, a classic example would be the interaction between the Earth and the Moon, for example. There's a force with which the Earth pulls the Moon, and there's a force with which the Moon pulls the Earth. And it turns out that even though the Earth is much bigger than the Moon, the two forces are equal in size. Now that seems a little bit odd, but no matter which examples you look at, if you have a ball been hit by a bat, the force of the ball on the bat is the same size as the force of the bat on the ball. Now, the consequences of those two forces on those two objects are very different. If I have a force that acts on a small object, there's a big acceleration results for that object. And if there's the same force acting on a big object, there's not so much acceleration. So the consequences can be very different. But the two forces have the same size. So we say forces come in pairs, mediating between two objects. A force is a vector quantity, which means it has magnitude and direction. And if an object has several forces acting on it, the forces combine to give one net force. So if I have an object and three forces are pulling it, we don't imagine it being stretched. We don't imagine that the object gets stretched. We just imagine that the object is rigid, and as far as it's concerned, there's only one force acting on it, and that's the net force. And if in fact these three original forces are perfectly balanced in terms of magnitudes and directions, so they vectorially cancel each other, then the net force, the overall force on our object is zero. I'd like to talk for a minute longer about this idea about the mediation, because this is where physics does have an amazing side to it. We tend to talk about physics like bookkeepers. We just want to know the answer. And so we tend not to particularly explain how the physics works. And the reason for that is the physics works in some amazing ways. So if I asked a particle physicist how the Earth pulls on the moon, when there's clearly no contact between the two of them, then what a particle physicist would say is that there is a particle that goes from the Earth to the moon and mediates. It causes a force to be felt. And that at first glance seems really strange. This particle, it's got a graviton, it's never been found in isolation. I can't show you a bucket full of them. It's a weird thing. But here's an analogy that might help. If I have two skateboarders and they're traveling along the road in parallel paths, and one of them has a backpack, and say the skateboarder on the right has a backpack and he throws it to the skateboarder on the left. Well, the thrower feels a force to the side, and the receiver feels a force to the side. And so you could say that the backpack acted as a mediating particle between the two objects, the two skateboarders, that resulted in a force. So there's something to think about. We don't dwell on that. We think about it and we pass on because we want to do the bookkeeping. But sometimes the bookkeeping is based on some amazing visualizations, some amazing realities that are sometimes hard to believe when you first come across them. So this next slide talks about the next step, which is Newton's laws. And basically, there's three Newton's laws. Most people know the order of them, so I'd like you to know the order of them. The first Newton law of motion: an object that does not experience a net external force does not accelerate. Okay? So if I have an object, here's an object, and maybe it's got a speed, maybe it's got a velocity, maybe it doesn't, but there's no net force acting on it, then it will not accelerate. And acceleration, as we've learned before, is the change of velocity in time. So this object will not experience a change in velocity as time passes. Well, if it's stationary, it stays stationary. If it's traveling at 1,000,000 miles an hour, it stays traveling at 1,000,000 miles an hour, unless a force acts on it. Now, that seems uncomfortable because we're used to a friction-filled world where we need a continuous force to cause continuous motion, because we're always trying to overcome the effects of air drag and friction. But it turns out, if we go to most of the universe where there's no friction, and we have an object that has a velocity, and we leave it alone, it will keep on moving forever until we apply a force to change that motion. It seems like we're getting something for nothing because we live in a friction-filled world, but in the vast part of the universe, that's exactly what happens. And we can say this mathematically, and we say the sum of the forces net external. That's important. We'll emphasize that later. The net force is the overall vectorial sum of the forces, and external means that it's got to be acting on an object in a system it cannot be internal to the system, and I'll illustrate that later. And this equals the mass of the object or the system times the acceleration of the object or system. If we look at this second law of motion, an object that experiences... oh, I'm sorry. Bang. Mathematically, we can say that the sum of the forces, this is net external, is equal to, well, I've put down MA. And I put down NA to emphasize the fact that this law still is obeyed. It just happens that the acceleration is 0 meters per second squared because there's no net force. So if there's 0 net force on a given mass, there must be 0 acceleration. Bang. We can write this law down mathematically, and we say the sum of the forces net external. Net means the overall vectorial sum of all the forces, and external means it's basically not inside the system. If I pushed a car from the outside, it would be an external force on the car. If I sat inside the car and pushed on the dashboard, it would be an internal force to the car. This has got to be an external force on the object. And I say, well, the net external force, the sum of the net external forces is equal to MA. And if there is a 0 net external force, there must be a 0 acceleration. So 0 equals the mass times 0. No net external force, no acceleration. If I look at the second Newton's law, it says an object that experiences a net external force does accelerate, and it obeys the F equals ma law. So here we have a visualization. Here's an object, and it's traveling to the right, but the force is to the left. And what happens is, as the force is applied, there's an acceleration. Constant force means constant acceleration. The velocity changes in time steadily, and so we may well simply reduce the velocity to the right to a smaller value. If we apply the force for longer, the object will stop, and eventually the object will start accelerating towards the left. But we're envisaging it here where we've simply reduced the velocity going sideways. Mathematically, we can say, well, the sum of the forces is equal to ma, just like we did in Newton's first law. But in this case, there is a net external force, and so there must be an acceleration for a given mass. In some ways, the first law and the second law are the same law, just in one case the net external force is 0, and in the other case the net external force is not 0. Newton's third law is a little bit different. What Newton's third law says, for every action force, this is action force, it's just we're calling it an action force, there is an equal and opposite reaction force. And so good examples would be my hand catches a ball. I could think of the force of my hand on the ball as the action force, and I could think of the force of the ball on my hand as the reaction force. A bat hitting a ball. I could think of the force of the ball on the bat as the action force, and I could think of the force of the bat on the ball of the reaction force. Even when they're not touching, I can have the moon and the earth, and I can think of the force of the earth on the moon as the action force, and the force of the moon on the earth as the reaction force. In these two examples, in the diagram, I have the force of a car on a concrete block and the force of the concrete block on the car. And I gave the example of the force of the earth on the moon and the force of the moon on the earth. And these forces form action-reaction pairs, and they are equal in size and opposite in direction. Now notice, I'm defining these forces by the two objects that are involved. The force of the bat on the ball, the force of the hand on the ball, the force of the earth on the moon. I'm talking about them in terms of the two objects involved. And if you ever want to know if two forces cause an action-reaction pair, then look at the name. So it could be the force of the tooth on the cake, and we'd have the force of the cake on the tooth. We could have the force of the hand on the strap, and the force we could have the force of the box on the table, and the force of the table on the box. If we name the forces by the two objects involved, there's no confusion. It actually is when we speak colloquially and we talk about the thrust force or the drag force or the weight or the applied force, we tend to lose the two objects that are involved in the action-reaction pair because we're speaking colloquially. It turns out that's understandable, because when we later on apply these net external forces, the net external force on an object will be one of these forces in the action-reaction pair, and I'll show you an example of that in a minute. Vectorially, if I have the force of object 1 on object 2, so force of object 1, let's say this in English, the force that object 1 causes on object 2, let's say it's gravity, and the force of object 2 causes on object 1, what we see is that these are equal in size, so that must equal that, and they are opposite in direction, and so we have that negative sign there to make the equal sign work. Good. There's some language we need to get comfortable with, some concepts, and one of the things we need to come to terms with is that we need to reinforce this idea of acceleration. An acceleration occurs when there is a change in speed. If there's a change in speed, acceleration must have occurred, and or there is a change in direction. That's an and or. Either one of these by themselves indicates an acceleration, but you don't need both of them. And there's absolutely no way you can have a change in speed that cancels out a change in direction. There's no magic combination that cancels each other out. They both, either one will indicate an acceleration, and both of them together indicate an acceleration. So we need to be comfortable with this. We need to, if I turn around to you and say there's a change in speed, you should recognize, oh, that means there's a change in acceleration. And if I say, oh, by the way, there's a change in direction, you should say, oh, that means there's an acceleration. And if I say there's an acceleration, you should say, well, either there's a change in speed or a change in direction, or both of those things occur. That takes a bit of practice. And then the second thing is, what is the net external force? And the net external force is the vector sum of all the forces. And if there is a net external force, then the vector sum must equal a number not equal to 0. I've drawn this as a one-dimensional thing. There's a vector f2 to the right and a vector f1 to the left. And we say the net external force exists if f1 does not balance f2. I'd like you to pay attention to this, and this is the, if you like, the logical sequence to go through. If there is no net force, there must be no acceleration. And if there's no acceleration, there cannot be a change in speed. and there cannot be a change in direction. If there's no change in speed and no change in direction, there cannot be an acceleration and there cannot be a net force. That's a law. That has to go together. If there is a net force, there must be an acceleration. It's not a possibility. There must be an acceleration. And if there is an acceleration, then there must be a change in speed and or there must be a change in direction. Either one or both must happen. And if there's a change in direction, well, we must have had an acceleration, so there must have been a net force. So that's a little logical sequence that we need to spend a bit of time learning. Let's do some examples. A baseball player hits a ball into the outfield. If the action force is the Earth's pull on the ball, Earth, ball. If the action force is the Earth's pull on the ball, we'd call that weight, wouldn't we? Then what is the reaction force? And just reverse the objects. The reaction force would be the ball's pull on the Earth. So the force of the ball on the Earth is the reaction force. Now hold on. We talked about a baseball player hitting a ball into the outfield, and we didn't even mention the bat, and we didn't even mention the outfield. And that's specifically there to make you visualize. It's not just a case of looking at the words and picking out the two dominant words and doing some trick to them. I deliberately talked to you about the player and the ball and the outfield to just occupy you and give you a visualization. And then I wanted to see, given an action-reaction force, did you know how to unravel it to get given an action force, did you know how to unravel it to get the reaction force? So watch out. So then, which is correct? The Earth's pull on the moon is more force than the moon pulls on the Earth? Or the Earth pulls the moon with the same force? More force? Same force? Or the Earth pulls the moon with less force? So here's the moon, and here's the Earth. And the Earth pulls the moon. Earth pulls the moon is that force, and the moon pulls the Earth is that force. That's an action-reaction pair. These must be the same because they are action-reaction pair. And there are lots of times when your intuition says that's not the case. The classic example is driving, and you get an insect gets battered on the windshield of your car. And you look and the insect is just broken to pieces and smushed, but the windshield of your car is perfect. It's as if nothing happened. Surely the force of the insect on the windshield must have been less than the force of the windshield on the insect. And it turns out, no, it's exactly the same. It's just that the reaction, the consequences of the force of the windshield on the bug is much more significant for the bug than the force of the bug on the windshield is for the windshield. So watch out for that. A plane is flying straight and level, cruising with a constant speed. So here's the plane, and it's cruising with a constant speed. So I can say that my velocity is constant. It's 150 miles an hour. And then which statement is correct? The plane is experiencing a net force horizontally. Well, if it experiences a net force horizontally, there must be a net acceleration horizontally. And yet we're told that the speed is constant. So if I have a force to the front, well, I do. I have the jet engines pushing to the front. but I also have the drag to the back. This is the force of the aeroplane on the air, and this is the force of the air on the aeroplane, action-reaction pair. Now, because these two are equal and opposite, they give no net force horizontally. So A horizontally equals 0. I'm going to say meters per second squared. So sum of the forces horizontally must equal 0 newtons. So the plane is experiencing a net horizontal force? I don't think so. The plane is experiencing a net vertical force? Well, it says flying straight and level. And if the plane were experiencing a bigger force upwards, let's say the lift force, compared with the downwards force, which is the weight, then its velocity upwards would increase because it was accelerating upwards, and you'd get the plane going higher and higher in the sky. So again, the plane is not experiencing a net force upwards, and it can't be both because they're both wrong. So it must be neither. So it's neither. There's a lot of conceptual physics in that question. Let's try another one. A car is cruising with a constant speed of 50 miles an hour as it goes around a large circular track. Let's look down from above. Here's the car. It's going at 50 mph as it goes around. Does it accelerate? And the answer is yes, it does. It's changing its direction. And it's changing its direction as time passes. So let's imagine it here. And we see its direction is there. So let's put that velocity on. And then let's imagine it here. And its direction is there. Well, let's say that velocity. Oops, a daisy. Let me do this right. That velocity. And so this is my V final. And this is my V initial. And my change in velocity is equal to V final minus V initial. So my change in velocity is that minus that. Well, we get the negative by adding the negative of V initial. This is minus V initial. This is V final. We added them together. And we get that is my resultant, and that is delta V. So for these two guys, my change in velocity points towards the middle. My change in velocity is in the same direction as my acceleration. So we say, does it accelerate? Yes, it does, but not in the direction of travel. Yes, it does in the direction towards the middle of the circle. Let's look at the other ones. Yes, in the direction out, away from the center. Absolutely not. No, it does not accelerate. Well, it does accelerate, but it's not in that direction, and it's not in that direction. It's in that direction. If you weren't too familiar with this vector diagram stuff, just go back and review the 4th module. We have vectors in that. Cool. A couple more things. Does this object accelerate? Let's look at it. Well, let's break it into components. We can say the sum of the forces horizontally is equal to +5. Let's make that the positive end. Let's make that the negative end. Added to, because it's the sum of the forces, -3, which equals +2 newtons. And the sum of the forces vertically is equal to, let's make this the positive end, and that's the negative end, +2. It's a summation, so let's add on to it -2, which equals 0 newtons. So we have a net force in the horizontal direction pointing to the right. So this is, does this object accelerate? Well, yes, the sum of the forces equals ma, so +2, is equal to 1 times A, so A is equal to plus 2 meters per second squared in the horizontal direction. Horizontal, 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 rather than vertical. So does this object accelerate? Yes, and it is 2 meters per second squared to the right. So there's the right answer. It's not 3 meters per second to the left. That's just the force, and it's not to the bottom because they are equal and opposite. And it's not 4 meters per second squared. I don't know where that came from. And no, it's that guy. Next, if the student pushes on a wall, action force with 10 newtons, the wall pushes the student with what force? And it must be the force of the student on the wall equals plus 10 newtons. Therefore, the force of the wall on the student is going to be, well, it's going to be the same magnitude, but in the opposite direction. It's going to be minus 10 newtons. I put down all positives here. I was talking about the magnitude, though I did not specify that, so shame on me. That should be a minus 10. Normally, a car tyre pushes on the road, that's the action force, with 100 newtons, and the road pushes on the tyre, the reaction force, with 100 newtons. Here we are. On an icy day, can the car tyre push on the road with 100 newtons? And the answer is no. You can't push on something that does not push back. I know that seems strange, but you cannot, and I can get you to demonstrate it to yourselves. Get a friend to drop a tissue paper in front of you and hit it, and you don't feel hardly anything with your knuckles, and yet you're hitting it, you're moving your arm as quickly as you can. You're doing what you feel would be a powerful force, a powerful punch, and yet you don't feel anything on your knuckles. But if you do not do this, but if you actually stood in front of a wall and went through the same physical motion, you would feel a tremendous force on your hand, which is why you shouldn't do it. You're doing the same thing. You're pumping your fist just as quickly both times. The physicality for you and what you're doing is the same. But in one case, the tissue does not respond to you, and in the other case, the wall does. So the wall is willing to push back, and so you can push hard on it, and you will feel that. Whereas the tissue is not able to push back, and so you do not feel the resistance, and so you cannot exert the force. Couple more things. A pickup truck pushes a car at 50 miles an hour along a straight and level section of 275. So here's 275, and I have a pickup truck, and here's a car. And they've got wheels, yeah, I know. And, you know, the car broke down, so the pickup truck came and just edged up behind it, and they're up to speed, and now they're going at 50 miles an hour. It's straight and level. Compare the force of the pickup on the car with the force on the car on the pickup. And I want you to pause and decide which answer you think it is. Is it the force of the pickup on the car is less than the force of the car on the pickup? Is it the force of the pickup on the car is equal to the force of the car on the pickup, and the force of the pickup on the car is more than the force of the car on the pickup? And I want you to stop for a second and commit and say which one you think it is. And then when you've committed, roll the tape. And the answer is that the force of the pickup on the car is equal to the force of the car on the pickup. And yeah, it's an action-reaction pair. You know, it's great. Yeah, that's Newton's third law. Force of the car on the pickup is equal to the force of the pickup on the car. They're equal to each other. No problem. Most people get that right. Let's look at this next one. A pickup truck accelerates a car. So a pickup truck accelerates a car. So we have an acceleration along a straight and level section of 275. Goes from 0 to 50. Compare the force of the pickup on the car with the force of the car on the pickup. Same choices. Force of pickup on the car is less than. Force of the pickup on the car is equal to. Force of the pickup on the car is more than the force of the car on the pickup. Now we've got an acceleration. And I want you to stop the tape and commit. And if you're with somebody, argue it out. And then when you think you got an answer, roll the tape and see where you are. And the answer is that the force of the pickup on the car is equal to the force of the car on the pickup, because it's a law. Now, that raises the question of where does the acceleration come from? If the force of the pickup on the car is equal to the force of the car on the pickup, where's the A? We need a net external force, and that's the issue. Because, let's be clear, the force of the pickup on the car is there. Force of pickup on car. And the force of the car on the pickup is there. And they are internal to this system, which is these two cars touching each other. It's like you sat in the driver's seat pushing on the dashboard. You're inside the system. Newton's second law, the sum of the forces is equal to ma. Well, that applies for net external forces. And so it doesn't apply to these two forces. So where does it apply? And it turns out that there's two other sets of forces we need to take into account. There's the force of the car on the air and the force of the air on the car. And this is, if you like, wind resistance at the front end. And then we also have, if you like, the force of the pickup on the road. That's the driving tire. And the force of the road on the pickup. Forces always come in pairs. We happen to have 3 pairs of forces in this question. And so we got to do a bit of thinking here. That's internal, so that's not what we're interested in. I'm interested in a force that's causing this object to move forward. That is an external force. The force of the road on the pickup. It's on the pickup. So that's an external force. And then we have the force of the air on the car. Hope you can see that. I'm going to do those in purple, so you make sure you can see them. So these two are the external forces, and when I add them together vectorially, I get the net external force. The green ones in the middle are internal forces, and these two forces, well, one of them is on the road and the other one is on the air. So those two are not part of our system. Can you see how there's a lot more to this than any old force equals mass times any old acceleration? You've really got to be analytical to decide which force counts, which force doesn't count. If you didn't get this second one wrong, don't be upset. It's like most people realize there's a problem in their gut because part of their head is telling them the net external force must equal 0, and there's another part of their brain saying, but there must be an acceleration. So if you felt that dilemma, you're right on track. Okay. So there we have it.